So the NH4 in this 49.A is acting as the acid, and water is acting as the base. Okay? And if we come over to the other side, right, now the acid on the reactant side becomes a conjugate base on the product side, because ammonia, weak base, could actually pick up a hydrogen to go back to NH4. And what we're left over with is hydrogen ions. Now, the other way this can be written here is technically we could write this as H3O hydronium ions. And I'll be honest with you, you probably are more likely to see it like hydronium ions than just the hydrogen ions there. Okay? So that's but these, just understand that these mean the same thing. This either however way this is written, whether it's just H ions or H3O ions, because what happens is the water molecule, right, has those lone pairs of electrons up here, and when you have hydrogen ions in water, they're going to be attracted to that negative lone pair. So that's why you get the H3O with a +1 charge. Okay? All right. And so if we look at that quickly, might as well. Right? Same thing with B, 76B. Get that on camera. It's this top one here. We have, this is, again, acetate, the acetate ion, C2H3O2. And we have a hydrogen attached to it versus water. So the acetate ion, when it has a hydrogen, acts as an acid, acetic acid. And water would be representative of the base. Okay? And over here, again, you could see this hydrogen ion written as hydronium, H3O positive. All right, so this becomes now, water goes from being the base to the conjugate acid, and the acetate ion becomes the conjugate base, because technically this here could pick up hydrogen ions. Okay, and then C for this one, HF and NaOH, that's the traditional, right? Hydrofluoric acid is got the H ion. Sodium hydroxide has a hydroxide ion. So again, though, you may be asked to recognize that on this side, let's see, on this side, technically, the NaF would be the conjugate base. Okay, why? And that's another good follow-up question. Thank you, Mr. Royks. Follow-up question. So here it is. Why would I say NaF would be? Why would I call that the conjugate base of this reaction? Any ideas on why that would be the conjugate base?
Wait, so does the acid go to conjugate base and then base?
The acid would become the conjugate base, and the base would become the conjugate acid. Here's why, right? What do we know about sodium hydroxide? Strong base. And so technically, what about the sodium? Soluble. So sodium actually acts as a spectator ion here. So if I remove sodium, maybe it would become more visible. What are we left with the fluorine?
Fluorine ion.
A fluorine ion.
So it'll accept the hydrogen.
Exactly, right? The fluorine ion would accept a hydrogen. And how do we know it would accept a hydrogen? Because when we think of our strong acids, Bic pens, it's not Bic phens, right? There's no F in there. So hydrofluoric acid is a weak acid, okay? So that means its conjugate base is a strong base. So actually, if we put fluoride ions, if we took sodium fluoride, if we had solid sodium fluoride in solution, okay, or we put it into solution, it would actually cause the solution to be basic. Why? Why would putting sodium fluoride in solution make it basic?
Because the fluorine would accept the hydrogen ions.
Yep.
It would take it
it would take it out of the water. Yeah, exactly. So the fluorine would actually, if I write this up here, we have fluoride ions reacting with water. Okay. Oops, book's falling off. We have fluoride ions reacting with water, and when they react with water, as Matt said, they're going to grab hydrogen ions, and we're going to end up with HF and leave behind hydroxides. So it actually makes that a basic solution. All right. Anyway, so that was that. 50. Let's see. I don't see. The next question I see looks like it's 55. All right, so 55. Come down here. What is the molarity of a solution of H3PO4 if 50 milliliters is titrated with 25.86 milliliters of a 0.1201 molar NaOH? Assume that all three hydrogens react with NaOH. So how have we been doing these types of reactions? How do you guys typically do these? In a neutralization reaction, do you guys try to do, because I know that 1 year, and I don't know if I did it last year, I did the M1V1, M2V2, okay? And so, I mean, there's a couple different ways you can do that. But if you look at this, this solution here, right, if you have 50, you have 50 milliliters, okay, of H3PO4, okay, and basically you're trying to figure out what volume of that H3PO4 you'd have to react. So in the reaction, there are, it would take 3 NaOHs for every 1 H3PO4. Why is that? Why would it be 3 NaOHs to 1 H3PO4? Yeah, well, yeah, because you realize that in order to neutralize in a balanced reaction, if we wrote out the balanced reaction, and believe me, don't do this on the test if you can do this in your head, but in the balanced reaction it would be NaOH plus H3PO4 gets us water and sodium phosphate. So if you can do this without writing this down, it's good. It's a time saver for you. So in order to balance this, we'd have to have 3 NaOHs and 3 waters. So in the neutralization reaction, it's 3 NaOHs to every 1 H3PO4. Now we have it in moles of NaOH, right? And based on the molarity, let's see, we have 0.120 moles per 25.86 milliliters. No, that's, I'm sorry, what is that? Hang on, I did that backwards. Yeah, I want to, what do I want to do? I want to multiply by the, right? Do I have this backwards? This should be 0.1201 over 25.86, right? And then solve. And what do we get when we solve? Someone have that answer or no? Let's see, it's 150, oops, 150 times 0.1201 times, whoops. is it 0 point rounded, 0.70? Is that what people got? Molar? Yes? Okay, good. All right, so that's 55. I think 58 is the next one that people wanted to look at. So 58. 58 talks about a, a 20.5 milliliter sample of vinegar. It's basically aqueous solution of acetic acid, and it has a density, if I can get down here, has a density of 1.061 grams per milliliter. The vinegar is titrated completely with 40.10 milliliters of a 0.40 or 4100 molar KOH. What is a percentage by mass of acetic acid in the vinegar? All right. So, how do we want to solve for this? Or what do we need to be able to solve for this? Can we leave it in grams? What's that? No, yeah, we have to take into account the molar mass, right? So bear with me for 1 second. I think they show you the work on these. Yeah, so they show you some of the work. So what you need to do is you need to first come up with a balance equation between the acetic acid and the vinegar, or excuse me, in the KOH. Okay, that's the first step. And so that is this balance reaction right there. Okay, then once we have the balance reaction, we can calculate out the moles of KOH by multiplying molarity times volume. And if we do that, we get this value here, 0.0644 moles of KOH. And as it says, since it's a 1-to-1 ratio, if we take the moles of acetic acid now, right, we've basically said, well, if we have this many moles of KOH, it would be neutralized by this many moles of acetic acid, or vice versa in terms of the neutralization, and then multiply it by the molar mass of acetic acid, which is 60.4 grams per mole, and we would get 0.9871 grams of acetic acid. So the question is percentage of by mass of acetic acid. So in this case, if we look at this, the mass of the vinegar solution is calculated out by using the density. So the volume of 20.05 milliliters times the density would get us to have 21.27 grams of vinegar, right? So the percentage by mass would be the mass of our acetic acid, the 0.9871 grams, divided by the total mass of vinegar, 21.27 grams, multiplied by 100, and we get 4.641%. Okay, so within that solution of vinegar, we would have 4.641% would be acetic acid. Okay. 59 is the next one. 59. So if we look at 59, we have excess silver nitrate reacts with 100 milliliters of barium bromide solution